Hi, this is Hsuan-Tien Lin. Thank you for coming to my talk. Today, I will talk about machine learning for modern artificial intelligence. Before we start, let me introduce a little bit about myself. I'm a professor at National Taiwan University and also Chief Data Science Consultant at Appier, a rising startup here in Taiwan. I'm a co-author of the Learning from Data textbook, and based on the textbook, I've taught 2 MOOCs on Coursera. I will start today by connecting machine learning with artificial intelligence. First, let's define intelligence. Traditionally, we view intelligence as the ability to think and act smartly. What do we mean by smartly? Well, one definition is to be like human, because human is arguably the most smart creature on Earth. And another definition is to be rational. If one can make rational decisions, then it must be super smart. And artificial intelligence is to ask computers to do this. Computers to think, computers to act, computers to be like human, computers to do rational things. And of course, in this definition here, we're implying that being smart means being like human and being rational, or means humans are rational. But let's ask ourselves, are humans always rational? The answer may be no. But let's look at an example here. Let's say we have self-driving car technology and developing, and after a few years, what do you want your self-driving car to make decisions for you? Let's say you're in your self-driving car and the car sees a swarm of people appear on the street in front of the car. The car then needs to choose whether to bump into those people and possibly kill lots of them, or to maybe detour its original route, giving you, the passenger, with a high probability while saving lots of people's lives. What decision do you want your car to make? Well, if you're really the passenger, you may want the car to act more like human. If you're hiring a driver to drive for you, then you really think the driver should put your life as the top priority. And therefore, if the driver puts your life as the top priority, it should save your and possibly other passengers' life by staying on track. It can bump you into a bunch of other people, kill them, and maybe the insurance would take care of that. On the other hand, if you want the machines to make really rational decisions, it may say, okay, all lives are created equal. Your life, other people's life, and so on. And therefore, even if you are the big guy sitting in the car, your life is as precious as other people's life. And given that there are 10 people in the front, maybe some of them are kids having a future and so on, we should save those lives. And sorry, we will kill you, the one sitting in the car, instead. Okay, so the car may be making fully rational decisions. And how would you want the car to react? Well, I deliberately put you in the passenger seat, so you're thinking from that perspective. But if you're thinking from the pedestrian's perspective, then you will say, okay, really, I want a super safe car that won't accidentally kill me while I'm walking on the street. Therefore, it's very hard to decide. It's very hard to decide which one is smarter. It takes, the society to decide what kinds of self-driving cars that we want. But basically, we can use this example to highlight that it's very, very hard for an intelligent agent to be both like human and thinking rationally, because humans may not be the most rational creatures on Earth. Okay, let's talk a little bit more about traditional artificial intelligence. As we mentioned, traditional artificial intelligence has 2 axioms. thinking or acting. And in thinking, there's the direction to be like human or to be thinking more rationally. Each aspect leads to a connected research field like cognitive modeling or formal logic. But those parts are not the main emphasis of mainstream AI nowadays. Mainstream AIs consider acting more. For example, if we want the computers to act more like humans, we have dialogue systems, we have computer vision, those fields of study. And if we want the machines to act more like rationally, we have the recommendation systems, we have advertisement, we have cleaning robots that we can think about. And those acting parts are attracting more attention from the industry and from academia nowadays. And that brings us to the new definition of artificial intelligence. Of course, that's mine. Okay, that's my modern definition. Traditionally, we want artificial intelligence to be like human or to act rationally. But those are traditional and very, very hard to fulfill. What's the possible modern definition? Well, my own definition is to be easy to use. Think about your smartphone. We call it smartphone. We think it's intelligent. Of course, there are some intelligent components like face recognition for unlocking or using voice recognition to decipher your commands and so on. But actually, what makes smartphone a smartphone is that they are easy to use, at least for many users. You can scroll on your smartphone, easily find the application you want, make the application do the things you actually want them to do, and so on. And those are the things that make smartphones. And following this, I want to make a new definition of modern artificial intelligence. I think modern artificial intelligence is more about applications. We can call it application intelligence. If we find the application easy to use, we call the application intelligent in some way. And if the application is super hard to use, then maybe it's not smart enough and so on. So if we look at modern artificial intelligence, really easy to use, being more like application is the key here. And we've seen lots of application intelligence in our daily life, like our cleaning robot, or maybe, the voice recognizer on your cell phone. Recommendation systems that's everywhere on the websites and also the ad systems. And of course, one of my favorites is an app on my cell phone that tries to tell me which wine is worth buying. If I'm in the supermarket, standing on a stack of wine trying to decide which to buy. That's Vivino here. And this kind of application intelligence is actually driven after years and years of research on artificial intelligence. Some of you may know artificial intelligence actually started dozens of years ago, and throughout of the years, it encounters some winters. The first AI winter that we encountered is after AI starts solving logical inference problems, and then we find that those problems are combinatorially hard, and at that time, the computation cannot handle all those. And then there's the expert-assistant AI that tries to encode what the humans are thinking, the domain knowledge of humans, and then we realize those systems fail to scale, given that there are just too many rules to be coded. Of course, we're in a different age now, and one may ask, what's really different here? Well, one thing that's different is that nowadays AI is driven by data. And now we can actually get more data because of the scaling of the internet, and also because we can obtain cheaper storage along with the advancement in computer science. And also in terms of hardware, there's faster computing for sure. Okay, there are different computational systems that allows us to do faster distributed computing and so on. And even on single machines, there are faster ways to do computing with hardware like GPUs. And also in machine learning, there are better algorithms after all these years of development, like the deep learning that you have heard of. And there's a healthier mindset after we suffered from the two AI winters. People now learn to make reasonable wishes to align what AIs can do along with what we want. And there are key breakthroughs that keep strengthening people's support, people's confidence on those AI systems. And in all this, the main important thing is that nowadays AI is data driven, and with more data, we can actually get better AI. I want to highlight an example here about how bigger data can tell us easier to use AI. Okay, some of you who are in the maybe elder generation may recall that in the old days, we don't really have GPS navigation systems. We have the very thick book of maps, and whenever we're traveling around, we look up the maps to decide which route to go. And in the first version of GPS navigation systems, what actually has been done was to digitalize those maps. And you can call those digitalization as the first version of the maps that people have built. After the maps are digitalized, then GPS systems can compute the best route from some A to B by the shortest path, and by calculating the shortest path from somewhere to another place. And that's the first version, and that already achieves some sort of artificial intelligence. It tells us a route smartly without having us, the humans, to look at the map. And what's the improvement with more data? Well, if the companies can gather more data on what the current traffic situation is like, for example, by leveraging the user trajectory, which tells us how fast users are moving on the map, or by leveraging some sensor technology that collects the traffic data to us, then we can compute the best route, not just by shortest distance, but by the current traffic condition. Okay, it would show that some parts of the road are red, meaning that there's traffic jam there, or maybe there's road construction and so on. And it computes the actual faster path for us based on the current condition. You see that this kind of AI is actually much smarter than the previous version, simply because it tells us actually a better route to achieve our goal. Well, what's the future? Well, if you're traveling a long distance, then the current traffic may not be efficient, because if you are traveling, for example, to a 4-hour driving distance place, then maybe after when you arrive there, then there's traffic jam according to the rush hours and so on. So what you really want the AI system to do is to predict the traffic, predict the future traffic that's happening. Can bigger data help? Yes. If the system collects enough data, like for seasonal variations year by year, for daily variations, between rush hours and non-rush hours, for weekly variations, like weekdays and weekends and so on. If there's enough data, then the system can make a prediction on what the traffic condition is like, and then give a route based on the prediction rather than the current traffic. I mark it for the future, but actually some of the companies are actually starting to try that. Basically, after they collect enough data, they can start building smarter systems to achieve the goal. So this is an example of a good AI system that can be improved by more and more data, starting from digitalized maps to current traffic conditions to years of traffic conditions that can be used for prediction. And the driving force connecting big data and artificial intelligence is the machine learning that we will be talking about in this talk. I'm not saying that machine learning is the only tool that connects those. But machine learning is the major tool. One metaphor that I often use is that big data is like the ingredients that we use for cooking. And artificial intelligence is the outcome, the dishes that we want. And machine learning contains lots of good tools and procedures that we can use to translate from big data to artificial intelligence. There are other tools, okay, for example, in control, in statistics, and so on. But nowadays, machine learning is one family of the main tools that people use, and that deserves highlighting here. I'm trying to highlight machine learning in our next slides, but I'm not saying that machine learning is the only way. Actually, the machine learning way is much inspired by the human learning way that I show here on the top. Traditionally, starting from data, for example, people observe years and years of financial data, or maybe years of medicine data, analyze them, and form domain knowledge about them. That's how doctors are trained. They are trained on lots of medical data that people have tried and succeeded, or tried and failed, and build on those to have the domain knowledge of doctors. And in one stage of AI, people try to encode those domain knowledge to build the AI as role-based systems. That's called expert systems. That's the route that we see on the very right-hand side. Machine learning is trying to speed up this process by following the bottom route. But it doesn't mean it's isolated from human learning. Actually, human learning can inspire machine learning by providing the method, by defining what mimics how humans are learned. If human learns iteratively, we can build similarly iterative algorithms. And also, the domain knowledge that humans extract can help machine learning have better models to conquer the problem. So there are methods that try to mimic human, and there are models that encode the domain knowledge. And that's the complete picture of modern artificial intelligence. And I'm not saying we should only follow the machine learning route. Actually, all the possible routes to achieve artificial intelligence are equally important here. Why is that? Because humans are actually pretty good learners in lots of things. For example, when there's very little data, machine learning cannot work that well. Current machine learning are built on the premises of bigger data. For smaller data, for some initial conditions and so on, human learning may be helpful. Human may learn faster. And also, if you are building an AI-driven product in the industry or just application intelligence, then really you want to choose the fastest way to achieve your goal. And any way to achieve your goal is as good as others, maybe even better than others if it can be achieved faster. So it is not to just stick with the machine learning way, but to think about all possible ways to achieve the goal. And often it is very important to think about how to leverage machine learning to help, leverage human learning to help machine learning. Because machine learning, when standalone, may need lots of data, lots of efforts to success. And if there are places that humans can help, then we can build the artificial intelligence or actually application intelligence much faster. Let me give you one example here. Actually, we will illustrate example more in our following slides. One application that we have tried is to estimate the tropical cyclone intensity. And our motivation was that meteorologists can feel and estimate the intensity from image. We know that. We know from our collaborators that they can do so. How do they do that? Starting from those images, they develop steps to analyze and build domain knowledge on what's going on. And of course, they can use this to build an AI system. That's how the current weather system works. But with machine learning, we can try something different. We can try to look at how humans see the image, okay, like how our visual system work, and have methods like convolutional neural network that analyzes the images. We can check with domain experts on what the domain knowledge is and encode those in our model, like rotation invariance. With the two, we can design good machine learning models to tackle the problem that's better than the current system. That's actually two of our previous works in the last few years that's accepted by a top data mining conference, that's KDD here, and a top meteorology journal. Now, for this second part of the talk, I want to tell you a little bit more about how my group drives machine learning research towards modern artificial intelligence, or application intelligence here. I will tell you three stories. The first story is about cost-sensitive multi-class classification, and the story is best illustrated by this hypothetical problem of trying to predict the status of the patients. Let's say the patient has three status: COVID-19 affected, cold affected, or healthy. This is a typical classification problem that tries to group the patients into different status. And the question we want to ask is, are all misprediction costs equal? If the computer makes an error, are all kinds of errors equal? Well, maybe not. If you think about it, if a patient is actually COVID-19 affected, but mispredicted by the computer or maybe by a doctor as healthy, the society pays a very high cost, as illustrated in the 100,000 entry in the table here. If the patient is actually cold affected but mispredicted as healthy, it's a big mistake, but arguably not as big as the previous one. Of course, we want the machines to be correct. So if the patient is cost affected, we want the machines to predict the patient as cost affected, and that's the zero cost one in the diagnose. But you see, different kind of predictions can be of very different costs, at least to the society. I made the numbers up, okay? So different people may have different numbers in mind, but for doctors, they have their own table in their brain built in, and therefore they would be very careful on the slightest symptom of COVID-19 in order to avoid, to prevent the society from paying a high cost. Now, if we were to build a computer-aided diagnosis system to help the doctors, then the system also needs to be fed the same table as the doctors, so it can be really helpful. So how can we do that? Well, this is the kind of problem called multi-class cost-sensitive classification problem, which is different from the regular classification problem that you see in textbooks. Starting from nearly 10 years ago, my group designed some different models for this kind of problems, ranging from support vector machines to deep learning in recent years. Now, after we have so many good models, okay, cool models in our opinion, we ask a question to ourselves, okay, we have these good models. Are people actually using them to build their cool artificial intelligence applications? Okay, are we achieving application intelligence with those models? Why or why not? Okay, to answer this question, let me first talk about the first issue that we were often asked by reviewers. Where do you get those costs? How do you get that cost matrix, that table that I showed you in the previous slides? Well, in the very beginning, my answer is it's not my issue. I'm an algorithm person. We design models, we design algorithms, and it's the user who should be worried about how to get those costs and feed to the algorithms, not my business. But then if you think about it, okay, if the users do not know how to get the costs, then application intelligence cannot be started. A few years ago, we got the opportunity to actually collaborate with human doctors, okay, to study the cost-sensitive classification problem for real application. The doctors want to classify bacteria, and according to the doctor, different kinds of bacteria have different needs for treatment. And if there's a misclassification, sometimes it's okay. If the two kinds of bacteria needs just similar treatment, then the misclassification is an error, but fine. But some bacteria requires very different kinds of treatment, and if you misclassify one as another, then there's a serious cost. So what we did was we got the cost table from two human doctors. Okay? We want to classify 10 different kinds of bacteria, so each doctor gives us a 10 by 10 table here. That's like 100 entries. We average the 100 entries from the two doctors and get this cost matrix here to feed to our algorithms. Now we can really answer the question about whether the designed model is useful for actual application intelligence. What's the result? Okay, let's look at the results here. The vertical axis is the test cost, and therefore the lower, the better. On the horizontal part, we have two different models. The red one is the traditional one. The orange one is the cost-sensitive one that we define. Okay, feeding the cost information, allowing the machines to generate a classifier that's hopefully closer to our need. And we see in this 2011 work, we actually designed a cost-sensitive model that's better than the traditional one. Great. Okay, we should be shouting out and say, you see, we have a super good model here. Now, everyone, please use our cost-sensitive model for your application intelligence. But did it happen? Well, if I ask this question, you can guess that maybe not so many people have tried our model for their application intelligence. Why is that? After we have this successful paper published in a leading bioinformatics conference, well, I went and asked our doctor collaborators about why they're not choosing it. And they tell us something. Okay, the cost-sensitive classifier that we have designed could achieve low cost, but it's at a price of making other lots of smaller errors, okay, smaller cost mistakes, okay, instead. Meaning, okay, it can achieve low cost, but comes with a higher error rate. And the doctor says, no, 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 no. I'm not going to work with an algorithm that's of 40% error rate. Okay, I just cannot do that. And this is illustrated from the figure here. Okay, we see that the horizontal axis, there's the error, the vertical axis, there's the cost. And our cost-sensitive classifier is in the red zone here, which is of high error rate, but low cost. While the traditional classifier, low error rate, but possibly high cost, because it may actually step into the bigger cost if it doesn't know about the cost information at all. What do we really want for our application intelligence? We want something of low error and low cost. And we want them both. Humans want them both. And therefore, we need to design something that goes to the blue zone here. That's called a cost and error sensitive classifier. Did we do that? Yes. So in our KDD 2012 work, we designed a model that achieves similar costs or similar or better costs, but significantly better error across different data sets. Oh, now we achieve cost and error sensitive classification. Great. Are people using those cool works for their application intelligence? Now I ask this question and you can guess, okay, maybe the answer is no. Why not? Okay, the answer is simple. The student, the research assistant for this work, graduated and went to the US for his PhD study, and therefore we closed this project and did not continue. That's where we ended to be. Okay, that tells us that achieving application intelligence is a very long journey. Okay, and there are many issues that can stop it from going. What are the lessons learned? Well, starting from as an academic person, we tend to think, okay, what's being more realistic is to be more generic. If I can have a model that solves all kinds of problems, okay, and then that's more realistic. But in application, maybe not. In application, people care about feasibility. For example, when we thought about our model, we didn't imagine how the users can input the cost metrics. And therefore, we ignore another big part of the cost for the doctor to spend their precious time filling in the 10 by 10 people, that 10 by 10 table of 100 numbers. The cost of inputting the cost metrics was not considered, but that's very important in actual application intelligence. And to really make application intelligence, it's important to have cross-domain collaboration, okay, because we do need the inputs from the doctors, okay, regarding the cost metrics, regarding whether it actually satisfies your need. But if you collaborate with humans in other domains, okay, you need to be aware that it's very hard to win human trust because humans tend to be multi-objective, okay, like being cost and error sensitive. And therefore, after you solve one problem, humans would want you to solve another. Okay? And that's the continuous journey to achieve actual application intelligence that can help humans. That's my first story. And in the second story, I want to tell you about active learning by learning. And active learning is a machine learning protocol that allows the machines to ask questions, much like how we want our students to ask questions in class. We will talk about a particular active learning protocol allowing the machines to ask questions about the label of some unlabeled example. The goal is to improve, okay, the classifier obtained, the hypothesis obtained with fewer labels by strategically asking the questions. And this is the protocol we'll think about. Okay, we will have a label pool of data and some unlabeled examples. And the iterative process of active learning will ask a question or will pick an unlabeled example in each iteration and obtain its label. After obtaining the label, the example is added to the label pool to train a classifier. And the goal is to improve the test accuracy of the classifier as fast as possible with respect to the number of queries. Now the question is, how do we query strategically? Well, there are several strategies you can use in real life, and then we can port those real life strategies as machine learning methods, as active learning methods. One strategy is perhaps to ask where you are most confused about. The other strategy is to guess, okay, what are the questions other people may be asking, and then try to ask this question, the most frequent one. And yet another strategy is to say, okay, this can be debatable. Okay, people can have different opinions about this. How about we ask questions, okay, surrounding this most debatable question? How about we ask questions surrounding this most debatable issue? And in active learning, those three strategies actually correspond to some different methods that people actually use. But choosing the strategy is not trivial. We show this in the figure here. Those figures come from three different data sets. And in each figure, there's the performance curve of three different strategies shown in different colors. On the vertical axis is the test accuracy, and therefore the higher the better. On the horizontal axis, that's the number of queries that we make. Okay, so we really want the curves to be on the very top, okay, or we want the area under the curve to be large. We see that in each of the data sets, the best strategy is different. Okay, the magenta strategy is the best for the first data set, but the worst on the third data set. Therefore, choosing one single strategy is highly non-trivial. And to achieve application intelligence, we need to ask, okay, how do we choose smartly? Can we let the machine choose smartly the best strategy for us? And we try to solve this problem in one of our works. The idea is to try and reward like human. When do we try and reward? If you go to a casino, do gambling with the bandit machines there, you try and reward. That means you go, okay, if you have several vending machines in front of you, what you may do is to try one vending machine, okay, put a coin in and see what kind of reward you get. If after trying several machines, you observe a machine that's particularly lucky, in your mind, you may give the machine more chance or have some strategies to decide what to do in order to leverage, okay, the better luck machine. We do the same for selecting active learning strategies. Basically, we give each strategy some probability to be tried. And after trying the different strategies, we decide which strategy is better, which strategy is better rewarded, and we continue with a higher probability for those strategies. That's basically the idea we do, okay? Mimic what human does in designing our methods. Okay? And that's called the bandit learning model. We reduce the problem of making an intelligent choice of strategy to the problem of making an intelligent choice of bandit machines, okay? And the latter is an established problem in machine learning called bandit learning. So what actually happens is that, okay, our algorithm, among the k strategies that it wants to select, in each iteration, it decides one strategy to be tried. After trying, we get the classifier and we evaluate how good the classifier is and feed this as the reward, okay, back to the bandit algorithm, okay, to decide the next round of machines to try. That's our AAAI 2015 work. And within the work, we have our proposed active learning by learning algorithm. So the algorithm is learning on the fly what the best strategy is. There's a reward design here, okay, how good the classifier is. And within that part, we use an unrigorous reward design. The original bandit algorithm was a theoretical one. Okay, there are theoretical guarantees and so on, but the guarantee requires the reward to be defined in a very restricted way. While we cannot afford to use the restricted way in our algorithm, and therefore we used not that rigorous design, but just to borrow the bandit algorithm and test it for our needs. Okay, what's the results we get? Okay, the three data sets that I showed you are these three, and in each data set, as we mentioned, there's no single best strategy. But if we look at our active learning by learning algorithm, that's the red curve here, we see that the red curve can keep chasing the best strategy. Basically, in the later of the iterations, okay, after many queries, the active learning by learning can be as good as the best strategy on hand, meaning it's making reasonable choices of the strategy. Great, so now we hope to achieve some sort of application intelligence. We're helping the users choose the best strategy on the fly. And based on that, we designed an open source tool to basically promote, okay, our algorithms. That's called LibAct, okay, an open source package here. Well, with the package, did we really make active learning more realistic? Did we really achieve application intelligence? The answer is maybe yes. We get more than 500 stars on GitHub, and there are continuous issues showing that people really care about the package. People really want to use their package for their applications, for building whatever works they have. And this is really the package that contains many strategies as well as the choice of strategies like ALBL, the active learning by learning algorithm. So we seem to achieve our goal. Okay, the package is designed to make active learning easier for real-world users, and achieving that should give us some level of application intelligence. On the other hand, the answer can also be no. Why is that? Because we may not have satisfied all needs yet. For example, I mentioned about many issues there, but the single most raised issue in our GitHub repository is that the package is very hard to install because we have used some C packages along with our original Python code and making it hard to integrate and install across different languages. And it's particularly hard to install on Windows or Mac. And that's the issue user care about. User doesn't care about whether you have the fancy active learning by learning algorithm. User care about whether it's easy to install. And also, although we have the active learning by learning algorithm, we see that in some applications, the algorithm, which is shown in light blue here, can be dragged down by bad performance of some strategies, okay, like the dark blue curve here. So the dark blue curve here, a very bad strategy. And light blue, active learning by learning, dragged down by that strategy. And when this happens, it may be simpler to just use one single strategy if you know which strategy is traditionally the best. Okay, that's uncertainty sampling. Okay, the dark green curve here, that's very, very close to the red curve that you can see. You don't need active learning by learning. You just choose uncertainty sampling, knowing that historically it can often have good performance and done. So people don't have an urgent need for selecting strategies, or they complain that selecting strategies may give them worse performance, okay, when doing those trial and reward process. And therefore, although we believe that the package is designed to make active learning easier, okay, it's a design. And for the design to match the need of real-world users, we need to evolve. We need to keep tracking new issues from the users, okay, to see how we can satisfy those. Okay, now lessons learned. Okay, first, for users, the scalability bottleneck of application intelligence is usually on making choices. We see in our previous example that's the choice of cost. Now we see the choice of methods, models, parameters, and so on. And seeing that, we try to design in the active learning space methods that help users make the choices. And we do so by thinking outside of the math box. Okay. Sometimes unrigorous usage may be good enough to design the algorithm that works. And I had this idea very early in 2012, but at that time, none of my students believed me. Okay? And I let this idea wait for a few years until some student is brave enough to try that, and then we succeeded and developed the package. Sometimes good ideas deserve patiently waiting. And in retrospective, easy to use in design is not always the same as easy to use in reality. Okay, so we really need sanity check from the users to tell us where to improve next. That's the lessons learned from this active learning project. Now, I want to quickly tell you a bit more about the tropical cyclone project that I mentioned earlier in this talk. And in this project, we try to mimic how meteorologists do in estimating the intensity from tropical cyclone images. When we started the project, we find that, okay, it's really hard to do so because there was no machine learning ready data set, and there was no model that uses the domain knowledge from meteorologists. So that's what we did. Okay? And we had the works in KDD, the Computer Science Conference. We had works in the Weather and Forecasting Journal. And what we did was the two I showed you. Okay, there's the convolutional neural network for mimicking how humans look at images. There's the rotation invariance borrowed from the domain knowledge in our machine learning model. And the question is the proposed model really better than the current weather system? The short answer is yes. The current weather system is the set count in the table here. And if we compare the rooming square error, it's lower. Okay, our proposed system, that's the CNNTC here, is achieving lower rooming square error than the current weather system. Great. Are people using this model? Well, people seem to be interested in trying, okay, but maybe not. Because, okay, one thing that we've heard, the SETCOM model, the current model is good enough. Okay, any error, rooming square error below 10 is good enough. So achieving from 9.66 to 9.03 does not mean that much to meteorologists. That's their current thought. And what are the lessons learned? Okay, I don't have time to go through every detail, but you can see, okay, first, okay, it's still important to have cross-domain collaboration so we can organize the data to be machine learning ready so we can get the domain knowledge to design our model. And also, it's not that easy to claim production ready, okay, to claim application ready, because, for example, our meteorologists still have concerns on whether the models can do well with unseemly strong tropical cycles, while they believe humans can do so. And good AI system requires both humans and machine learning, okay, as the figure that I showed previously. And it's still an art to blend the two, to take people from the two sides to work together to build good AI systems. Okay, those are the three stories that I want to tell you. And in the very last part of the talk, I want to quickly go through machine learning for future artificial intelligence, my thoughts on them. Okay, in 2010, 2015, those are the rising age of artificial intelligence. And that's the age where AI becomes promising. Okay, like we have very mature super vector machine models, we have deep learning models that start to make initial success. I call this age the AI or for the application. Okay, so you have the original application by whatever technique, and you can use the original technique or artificial intelligence, or you can try artificial intelligence. So in this stage, okay, whether to use AI or not is really a choice, okay, that application people can make. Okay, they can decide to use so, they can decide not to use so. In the age we have now, it's the AI plus age. Okay, people are trying to use artificial intelligence to be added to their application. Okay, to build new application directions that are helpful. And that's the age where AI becomes competitive because it achieves superhuman performance on some tasks like Go. And also all the big tech companies become AI first. Okay, they want to build AI technology, they want to use AI technology in their applications. And what about the next years? I'm calling the next years the AI times year. Okay, basically, you need AI to be on top of your application. And if you have zero AI, no, you don't have any good applications because your value of the application certainly becomes zero. That's 0 times anything is 0. That is, AI becomes necessary. And I'm quoting a dear friend of mine's words. You will not be replaced by artificial intelligence, but by humans who knows how to use artificial intelligence. Okay, people need to use artificial intelligence for every application that they see in their daily lives. That's what I see now and next. And for future AI, it's going to be more creative to win the human's respect. Okay, like at APIR, we had an earlier work on designing matching clothes. Okay, so that's the creativity part. And when AI becomes creative, people respect it more because creativity was originally believed to be something reserved for humans, while if machines can achieve it in some decent way, people love it. And AI needs to be more explainable because human needs to trust some of the decisions that AI makes, for example, in self-driving cars or in the law domain or maybe in the medical domain. And one of my students work on automatic bridge bidding, designing, letting the machines decide its own bridge bidding protocol is a very interesting one to achieve explainable AI. And also AI is becoming more interactive because many of the AI would need to be humanly, remember? Okay, and in this humanly part, we really want AI to have the ability to interact with humans seamlessly. And one of my students' work collaborating with the company DeepQ is to have efficient disease diagnosis, basically a computer doctor that tries to ask, okay, you the symptoms that you have as a patient and decide what kind of disease that you have, and doing so in an efficient way. Those are some of the examples about how AIs are evolving to serve human needs, to serve application needs better for the future. Okay, to summarize, I told you my view about machine learning and modern artificial intelligence. And basically, machine learning is the tool, and if we add the tool properly with human knowledge, we get easy to use application, and that's modern artificial intelligence, application intelligence. And for achieving modern artificial intelligence, we need to do good machine learning research. And lessons learned is that through those research, we need to be more open-minded in collaboration, in how we evaluate our performance, in our methodology in achieving artificial intelligence. And for the future, it's very crucial to be human-centric, to think about what kind of applications we need, what kind of applications humans will be satisfied, humans will find easy to use. And those are the growing directions of artificial intelligence. Thank you very much again for coming to my talk today. And now I'm ready for some questions.